Hello everyone, my name is Stephanie Woodruff, and today I'm excited to show you how we can create instant ice. We'll be exploring phase changes and how different catalysts can force water to freeze instantly. We'll attempt 4 different methods to make instant ice and discuss why these phenomena happen from a chemistry standpoint. Remember, it's okay if the experiment doesn't work perfectly every time. The key is to understand the process and make observations. So let's begin by going over the materials that we're going to need. We're going to need several bottles of water. I'll be using 4, a freezer, 2 clear glasses, some ice, and a bowl. Before we can begin our experiment, we first need to place our unopened water bottles in the freezer. We're going to leave them undisturbed for about 2.5 to 3 hours. You want them to be super cooled, just on the verge of freezing, but still in liquid form. Before we dive into the methods we'll be performing today, let's talk about supercooling. Supercooling occurs when water is cooled below its normal freezing point of 0 degrees Celsius or 32 degrees Fahrenheit, but remains in liquid form. This happens because in pure and undisturbed water, there are no impurities or disturbances to act as the nucleation sites, which are necessary for ice crystals to form. Without these nucleation sites, water can be cooled well below its freezing point and still stay liquid. This is the principle behind our instant ice experiments. From a chemistry standpoint, supercooling takes advantage of the delicate balance between temperature and the kinetic energy of water molecules. In a stable state, water molecules move freely and are kept apart by kinetic energy. As the temperature drops, this kinetic energy decreases. But if the water is undisturbed and pure, it avoids forming the structured lattice of ice, remaining in a liquid state. Now to get started, I need to go to the freezer, grab some of my bottles of water, and we'll begin with method 1. Bear with me in just a minute. Okay, so here is one of our bottles of water from the freezer. And for method 1, we will be performing the flash freezing in the water bottle. We need to carefully remove a bottle from the freezer, hold it up, and give it a gentle but firm tap on the side. So I'm going to hold this up here for you guys. You can see it's still in its liquid state. And let me try to just put a firm knock. Okay. That didn't do anything. I don't know if I'm doing it hard enough. Bear with me here. Okay. Let's see what happens here. From the video I watched, it was just kind of a jolt. I feel like the water bottle is. Oh, and it is starting to freeze from the top. I think I just didn't do it quite hard enough. I don't know if you guys can see that. Okay. Let me see. Let me turn this around here. It is freezing from the top and going down. When the super cold water is disturbed, it triggers the rapid formation of ice crystals. And this happens because the disturbance creates a nucleation site, a point where the water molecules start to arrange into a solid structure. As we can see, it took a little bit more force than I was expecting. We do still have a little bit of liquid here. A liquid state of the water. There is quite a bit of ice inside of our bottle here. And what that tells me is I probably needed to leave it more, maybe around 3 hours. I got this out about at 2 hours and 45 minutes. But this was not a complete failure. As you can see, we do have ice in our bottle of water. There is still some liquid water though. And this process, it releases latent heat, which helps continue the formation of ice throughout the bottle. The disturbance reduces the activation energy barrier needed for nucleation, allowing the supercooled water molecules to align into a crystalline structure quickly. So, still pretty neat. I did have to put some force onto the bottle, more than what I kind of expected. But again, it may be because our water needed to be in the freezer just a little bit longer. But I'm hoping you guys can see that. There is ice that is all throughout our entire bottle of water. It's not frozen solid, but it is, we do have ice here. Okay, let me grab one of our other bottles of water and we're going to keep moving on. Okay, so next we're going to try pouring some of our super cooled water over ice. I just grabbed another one of our bottles of water out of the freezer. You can see it is still in liquid form. And I went ahead and got a bowl full of ice. Now you need to prepare a bowl of ice cubes and get another bottle of water. And be sure to open the water bottle gently and slowly as we pour the super cooled water over the ice cubes. So we don't want one of our flash freeze in the bottle happening here. Took a little more force than I had anticipated initially. Okay, we have our water, we have our ice cubes, and let's slowly pour that. Wow, you guys see that? Be sure I'm holding that up in the camera for you guys here. We could make snow cones at home, or our own ice sculptures. We're starting to overflow in our bowl here. It may be a good idea to use a little bit larger bowl than what I did. But you guys can definitely see there that, bear with me because I made just a little bit of a mess on my computer. As the super cold water comes into contact with the ice acts as the nucleation site. The water molecules near the ice rapidly form ice crystals, and this process continues as the water pours over more ice. The existing ice helps to start the freezing process fairly quickly, almost instantly, when the water touches the ice cubes. The ice cubes provide a template for the super cold water molecules to arrange into a solid state, facilitating a rapid phase transition from a liquid to a solid. Okay, so now our next method that we're going to try is to pour one of our bottles of water into a glass and place an ice cube in it. We're going to take another super cooled water bottle and a clear glass. We will also need to have ice cubes ready. We're going to begin by pouring the super cooled water into the glass and then drop an ice cube into the water and observe what happens. We're going to carefully open this water, making sure we don't get a flash freeze to our water bottle. Okay, let's take our clear glass here. Let's pour water in that. And I'm going to get an ice cube. And let's drop this down into our water and observe what happens. Okay, as we can see, we're pretty much 3/4 of the way frozen. We do still have a little bit of liquid, and again, this makes me question, did this not freeze completely solid due to the fact I only left our super cooled water in the freezer for about 2 hours and 45 minutes, wondering if 3-hour time mark would have helped in our experiment. Now, when the ice cube is dropped into the supercooled water, it provides the nucleation site. And the contact with the ice cube causes the water molecules around it to start freezing immediately, which that did start to happen. I immediately saw ice crystals. And it speeds rapidly through the rest of the water in the glass. This is another example of how nucleation sites trigger the phase change from a liquid to a solid state. The ice cube lowers the energy barrier for nucleation, allowing supercooled water molecules to transition into a solid lattice structure around the ice cube. And around this entire ice cube, you can see that there is ice all around it. The longer I've left it sit here, we're getting a little bit more liquid. Let's see what happens if I add in. Oh wow, just like on our example a few minutes ago, or a second ago, when we dumped our cooling water on the ice, we're getting that same type of, I don't know if you guys can see that very well. It's kind of hard to see here, but as I was pouring the super cool water onto the ice inside the water, I just wanted to see what would happen there. And it was pretty much the same thing that we observed when we just poured the water onto our ice cubes. So now we're going to be getting into our last method, and we are going to pour water into a glass, holding an ice cube halfway into the water. Let me go and grab our final bottle of super cooled water. Okay, so now we're going to need to take our last super cooled water bottle and another clear glass. We will also need to have an ice cube ready. And now we're going to pour the super cooled water into the glass and hold the ice cube halfway into the water and observe what happens. So we are going to dump this water into here. And we're going to hold an ice cube halfway into the water. Oh. And you know what, guys? I think I actually grabbed the wrong bottle of water. Bear with me here. Let's see if this is in fact it. Uh-oh. Oh, we have some ice cubes that are stuck together. Okay, so our final experiment actually did not hold into place as I predicted or hypothesized here. And again, I do believe this was, well, first of all, I accidentally grabbed the wrong bottle of water when I initially went to do this, and that was a human error. And then I thought, okay, well, maybe I'll use this other bottle that we just previously used, but I think it set out a little too long. It actually was barely working as it was. As far as the temperature, I think needed to be just a little bit colder. Again, I kept my bottles of water in the freezer for about 2 hours and 45 minutes. I would highly encourage you to check around 2.5 hours. I guess it depends on your freezer. But for mine, I think 3 hours would have been the exact mark of when I should have taken the water out. So for our last example here, I actually just don't have any more bottles of water on hand that I have frozen. So sometimes we're going to have failed experiments, and that's okay, because what we're doing, we're always learning, right? And we're learning the chemistry behind it. So holding the ice cube halfway in the water, it provides a controlled nucleation site, and the water molecules near the ice cube will begin to freeze, or should begin to freeze, as you hold it. And you can see the freezing process start at the contact point and spread out. And this controlled method helps to illustrate how nucleation sites work to start freezing. By holding the ice cube halfway, you can visually observe how nucleation begins at the point of contact and propagates through the supercooled water, demonstrating the exothermic nature of the freezing process. Unfortunately, our fourth attempt, our fourth method, did not go as planned. A lot of that was human error in grabbing the wrong water bottle and then leaving my other one sit out a little bit too long to room temperature. Also, yet again, needing probably a little bit more time in the freezer, maybe about 10 to 15 more minutes. If the experiment by chance does not work as expected, there could be several reasons as to why. The water bottles may not have reached the right temperature, so make sure they are super cooled, just below freezing, but not solid. If the bottles were disturbed while in the freezer, ice crystals might have started to form prematurely. It also could be due to impurities in the water, which can prevent supercooling by providing nucleation sites before the water is supercooled. Also, leaving the bottles in the freezer for too long or not long enough can also affect the results. To wrap up, we've explored 4 different methods to create instant ice: flash freezing in a bottle, pouring water over ice, dropping an ice cube into supercooled water, and holding an ice cube halfway in the water. Each method relies on the concept of nucleation sites to trigger the phase change from a liquid to a solid state. Even if some attempts do not work perfectly, it's important to understand the science behind it and make the observations. Thank you so much for joining me in this fascinating exploration of phase changes in water. I hope you enjoyed the demonstration and learned something new, I know that I did, about the chemistry of freezing and water. Thanks again.